We have the next module, lecture 5B1, in which I just talk about energy and force in presence of dielectrics. Now, we have already done electrostatic energy in any particular charge configuration. The question is, does any of that gets modified in presence of dielectrics? So we have earlier calculated the electrostatic energies stored in the field as epsilon by 2 e squared d tau, or half v dq. Half v dq can be as rho v d tau for continuous charge distributions. Now this was in terms of field variables, and this is in terms of source variables, okay, assembling charges of our source variables. These were the two extreme. We had even two more other independent ways of doing it, or related ways of doing it. And this was for any charge configuration. And rho is all charges, and rho is field. So why do we need any other method that we have in dielectric? But we know that for a dielectric, we have a new field variable, that is d, for which the sources are specifically free charges. So a possible intuitive extension of the above field energy is that you take this epsilon inside and use one of the E here to epsilon E to make it D. So half D dot E d tau. So then it looks like I can use my D and E together to get the total energy. So in expecting so, of course, you are assuming that it's the linear dielectric. Where did I assume that? When I said epsilon E is equal to D. D is equal to epsilon E. Okay, so is only for linear dielectric. That's what I would expect. We know that different energy expressions have to be interpreted differently depending on the physical question being asked. Specifically, while accounting for work, which work is being included in that and which is not being taken into account. So that it requires careful physical considerations. Okay, but anyway, let me go. So electrostatic work done. So remember, the answer depends on what the process is of doing the work. Okay, so the final equivalent charge distribution will, of course, have the following stored energy, which you have already done. Okay, suppose I'm given a charge distribution, and this is the final charge distribution. And what is the energy, electrostatic energy stored that we have already worked on? That is this. But assembling the free charges should include the work done by the material in responding with bound charges or work done by the free charges to polarize the material by whatever mechanism it gets polarized. That is the work done by the binding forces or the spring forces. Now the question is, can we simply modify the charge distribution by considering, so this is the charge distribution given, so this charge distribution is simply modify from rho to rho f, I know this, okay, and replacing rho f by the divergence of d. Is that simply allowed? Now this would not be true in general, okay, but it holds for linear dielectric for d is equal to epsilon e. That is, you can replace, okay, but we'll have to go through the process to realize that. So we take the route of bringing small amount of delta rho f, okay, to increase rho f gradually. So we assemble free charges, but while every time I bring the free charges, a little amount, okay, I let the material respond with its bound charges as well. So the work being done by the polarized body is also being taken account, okay, in the process. So the procedure is work done in gradually assembling free charges with the dielectric responding. Okay, so let's look at the change in energy, delta W. So I only take delta rho f and V d tau. That's of course true that at a potential V, I bring in this amount of free charges. But remember, this V is due to all charges, not just free charges, okay? Because potential would be because of both the free charges and the bound charges that come into place. So, and I can now write down this in terms of divergence of delta D. There's a little bit of delta rho F. I can always express that as divergence of delta D. Rho F is divergence of D, but since there is only a delta amount, I take divergence of delta t, V down. Now this clearly uh, implicates that I should look at the divergence of this and this product. If I do that, okay, then divergence of delta d into V, I can expand it, okay, then this part I recover, okay, the one that I'm interested in, plus divergence or del d dot del V, and hence I can write down this in terms of these two, okay, which is like partial integration. So I can write down in terms of divergence of the product of delta dV, and this minus, okay, will come down this here and become plus, and so the del of d dot e theta. Now, this is a term, okay, which is, I can use divergence theorem because divergence of the whole quantity over a closed surface, which can be made arbitrarily large for all space. We have done this earlier and thus made to vanish because I am looking for delta W in all space. And in all space, the contribution here would be very small and negligible. And hence I'm left with only this, okay, delta W is delta change in d dot e d theta. Now, this is valid for any dielectric, whether it is linear, non-linear, so far. Okay, going forward, I can make something for linear dielectric only. For linear dielectric, I can always assume that d is epsilon e, and hence delta dE I can express in terms of, I bring it in terms of epsilon e, and then becomes half delta of epsilon e square, which I can always write down as epsilon delta e, okay, dot E, and which is delta D dot E. So I express this in terms of delta D dot E in terms of half delta D. Okay, so the change in energy because of linear dielectric, because I brought in this small amount of free energy from here, is over all space, is this delta amount of half of D dot E. So if I integrate, okay, then I'll get the total amount, and that is W, okay, or WE, if you can call it, half D dot E theta. So that was the expected energy expression, but we had to go through this process. Till this far, it was any dielectric. Then I make an assumption about linear dielectric. Then I get to this. Okay, so so is this expression is not valid for nonlinear dielectrics. Why? Because their dissipative system, since is nonlinear, then the process of charging might involve processes which are like friction-like. So there could be loss to heat energy or other forms of energy. So friction-like losses are involved. This is only true for linear materials where the energy stored is still all electrostatic. So let's take the force, okay. Now, system with fixed charges, this is a method of virtual displacement. So once I get energy, the getting force through energy in presence of dielectrics is the right method, okay. We'll see why. So consider an isolated system of conductors and dielectrics with fixed charges, and let there be a virtual displacement. The method of virtual displacement says that I don't make a real displacement, but I say if I assume if I had made a DL, then I have to, the force should be acting on that and take that into account and then use that to obtain the force. Okay, you might have done this already in while calculating some of the forces of the northern hemisphere and southern hemisphere charged bodies. Now, dW is, let's say, this is the force under constant Q condition, okay, is a total electrical force under constant charge condition, and let DL with the virtual displacement, as I said, okay. Then FQD dot DL, but dW must have come, this work must have come at the expense of the electrical energy, okay, and so this must be equal to FQD dot DL but minus DWE. Now, but this DWE is a scalar quantity. I can always express this in terms of a gradient of WE dot DL. That's the expression that we already know, that any differential amount of a scalar is the gradient of the scalar in the direction of the displacement. All right. So being an isolated system, this must have come from stored electrical energy, this one, okay, as already have said. But since DL is arbitrary, okay, so if DL is arbitrary, so if I compare this, and this. Okay, that which means the gradient of WL must be FQ. Okay, so that is the simple derivation of the force. Okay, so if I know WE, and then now since it is grad of WE, gradient of WE, I can obtain FQ in x direction in Cartesian coordinates simply del by dou x of WE minus dou by dou x of WE or Fx. So this is something like the potential energy that you already had done, obtained forces in your earlier course. Okay, now let's come look at the force of system with fixed potential. Okay, here there is a complication. Why? Because to keep the bodies at fixed potential, a source must be there to keep doing the work, to keep them at the potential. So if you take that into account, then it will be fine. Consider a system connected to sources, okay, of conductors and dielectrics, such that the potentials are kept fixed. Now let dl be a virtual displacement as last time. So the total electrical energy stored must be the work done by the force under constant potential, okay, and the work done by the source. All right. So where this is the force, the total electrical force under constant voltage conditions, and dWs is the total work done by the source. Okay. So work done by source in this case. So each at a potential V is constant potential V. I am adding dQ. So the work done is dWs V dQ, and energy stored is of course dWV is half V dQ. We know this. All right. So I plug that in. So this is the source of the battery. You can see already does double the work to keep the voltage the same. This is half VDQ and this is VDQ. Okay. And so if I write this down in terms of dWe minus dWs, and this I know is half, so it's minus dWe. Again, I do the comparison with, I can write down this in terms of the gradient of total dE minus dE dot dl. dl is arbitrary, and this is the mathematical expression, and hence my conclusion is the same. Okay, there is a force under constant voltage minus gradient of WE, and it came out to be same as the constant charge method, provided you took the work done by the source into account. All right, you'll be falling into a trap. Obviously, the force cannot be changing depending on the different electrical constraints that you are imposing. Okay, so the same as a constant charge case. So it is of course easier to work with constant charge case since you don't have to worry about the work done by the source. Okay. So now let's take a force in the case of a standard case of parallel plate capacitor. Remember, a source also does work to keep the potential. All right. So this is consider a slab of dielectric, okay, of susceptibility chi e, partially inserted into between the plates of the parallel plates capacitor. Okay. The length is L, width is W not shown here, and separation is D. Okay, so let's take the constant charge case. In constant charge case, of course, WE is equal to half CV squared, which we know. So, and we can find out the FQ minus W by dx. So x is changing. Then half Q square C dC by dx. And that is nothing but half V square dC by dx. This is simple. So the force is this. So now calculate C as a combination of this air capacitor and the dielectric capacitor, which is easy. So epsilon W is the width, and the full capacitor minus this minus chi e x. X is this amount. Okay, L is the full amount. So epsilon r L, if everything was the slab dielectric, but it is not, and hence capacitance is this. And from here I can calculate dC by dx. Okay, and that is chi e epsilon W naught d. And so the force can be easily plugged in dC by dx, and force is in the minus x direction, which means it's getting pulled in, which is the case in any case for any dielectric. Okay, the force is attractive because the bound charges are want to be close to the free charge. If there is a plus charge, then minus charge would form next to the plus charge, and hence there is attraction, just as in the case of the conductor. Uh, so let's look at the constant V case. Okay. So dWe, I have to take into account this, the VdQ is the source. Okay. Total electrical energy, FBdx plus VdQ. So FB, okay, I now replace by minus dWx VWS, okay, by just differentiating. And that comes to one part giving me minus half V square dC by dx, and this giving me V square dC by dx, and hence the total is half V square dC by dx, same as here. Okay, the force comes out to be the same. Okay, and it is the same formula. So the energy method works because of E being conservative. It takes care of even the fringing field. Okay, so what is actually pushing this in the minus x direction? F is minus. Okay, so in this direction is the fringing field. Otherwise, the field is inside. This is perpendicular. Okay, so that cannot be the work done in and the displacement is in this direction. So this force cannot be doing the work. The work is being done by the fringing field, which has a component. Okay, so energy method makes, but I'm not calculating the fringing field. How did I get the effect? Because the energy method works because E being conservative, it takes care of even the fringing field, whose component is the one which pushes the dielectric slab in. That's important to realize. This is really we're taking the help of the consistency of electrostatics, okay, without solving for actual fields of lines everywhere, okay, and we get that result simply from energy. So for in presence of dielectrics, it is um, it is important to use the energy method to obtain the force. Let's take me an example of this is just a energy calculation. A spherical conductor of radius r, radius a, carries a charge q. It is surrounded by a linear dielectric material of susceptibility chi e out to a radius b. Find the energy of the configuration. All right. So obviously we need to use this formula. That is, since there is a free charge given Q, I can calculate D everywhere. Once I calculate D, I can calculate E everywhere and then calculate this total energy stored. Okay, so this is the physical situation. There's a conductor of radius A and it's surrounded by a dielectric of radius from A to B, and it is susceptibility chi. Okay, this is a standard. So it is a conductor, so D is equal to 0 for R less than A. And for anywhere else, it depends only on source charge. It is Q by 4 pi R square for R greater than A, whether it is inside the dielectric or outside. So once I know D, I can calculate my E everywhere. Okay, so E is of course 0 less than A, and this is Q 4 pi epsilon, okay, because it's inside the material between A and B. And this epsilon is epsilon naught in free space. So I know E, I know D, the W is a straightforward calculation. All right. So write down half D dot E d tau and replace DE here. So this R less than A, of course, gives a contribution that is 0 because E is 0, D is 0. Then I am worried about the contribution from the first term, that is A to B. Okay. Here, of course, is 1 by epsilon, and then R 1 by R square, 1 by R square, 1 by R square, each term coming from one from D and one from E, R square dr, and 1 by epsilon naught B to infinity. This is A to B, B to infinity. That is 1 by R square dr uh, coming from E. All right. And then I this integration is the same in both cases of A to B, except that one is 1 by epsilon, the other is 1 by epsilon naught, and hence I get my total energy in terms of epsilon and chi e. But the question is given in terms of susceptibility chi e, and hence I should re-express this in terms of susceptibility chi e, and W is Q square, so epsilon naught 1 plus chi e, 1 by A plus chi e B. It's simple. The method is to illustrate that in presence of a dielectric, I didn't have to know the charge configuration due to bound charge here or the bound charge here to obtain the energy. So this formula facilitates simply knowing D and E, I don't have to worry about bound charge. Of course, it works because it is linear dielectric. All right. So with that, we come to end of this module. In the next module, I talk about polarized bodies in electric fields, in external electric fields.